Welcome to a deep dive into the world of diffusion models. You sent over this research paper
Yeah.
that dives into how these models can actually get better results by using more processing time even after they're done training.
It might seem counterintuitive, but
Yeah.
it's a really exciting area of research in AI image generation.
So we're talking about diffusion models, which you've probably heard of because of their popularity in creating images from text prompts.
Right.
But this paper isn't about the basics.
Yeah.
It's about getting more out of them.
Right.
What makes them different from other generative models when it comes to this inference time scaling?
Diffusion models have a unique advantage because they can flexibly use processing power when generating images.
Okay.
Unlike GANs or VAEs, they're trained to approximate something called a vector field.
Hmm.
That means we can evaluate them multiple times at different noise levels for each image generation.
Okay, that sounds pretty technical.
Sure.
Can you break down this vector field idea and how it allows for this flexibility?
Think of it like this.
Okay.
Imagine you're trying to sculpt a perfect image out of clay.
Okay.
Instead of starting with a solid block,
Uh-huh.
you begin with a cloud of clay dust.
Okay.
The diffusion model gradually refines this noise into a coherent image.
Hmm.
The vector field is essentially a map that guides this refinement process.
And the more we can explore this map, the better the final sculpture.
Essentially.
Oh.
This research paper delves into how to find the optimal starting point in this noisy cloud that will lead to the highest quality image. It's like searching for a hidden gem within a vast landscape.
So it's not just about throwing more computing power at the problem blindly.
No.
It's about strategically using that power to find the best starting point for the image generation process.
They call this starting point the perfect noise.
The perfect noise.
Yeah.
How do we even know what that looks like?
That's where things get really interesting.
Okay.
This paper introduces something called verifiers, which act as judges during the image generation process.
So instead of relying on human judgment to say whether an image is good or not,
Right.
these verifiers provide automated feedback.
That's right.
Okay.
These verifiers are AI models themselves, trained on massive data sets to evaluate image quality based on different criteria.
So we have these automated judges assessing the images.
Yeah.
But how do we actually find those perfect noise candidates to feed into the model?
The paper explores different search algorithms that work in conjunction with the verifiers.
Okay.
It's like having a treasure map and a metal detector working together to find the buried treasure.
Okay, I'm starting to see how these pieces fit together.
Mm.
So we have the diffusion model itself, the verifiers judging the output, and the search algorithms exploring different starting points.
Yeah.
But how effective are these different algorithms?
The research shows that there's no one-size-fits-all approach.
Okay.
The best algorithm depends on the specific task, the chosen verifier, and how much computational power you're willing to invest.
So it's about finding the right combination of tools and strategies for the job.
And what's fascinating is that the performance of these algorithms can sometimes lead to surprising results.
Okay.
In fact, one of the key findings is that smaller diffusion models, given more inference time and the right search strategy,
Yeah.
can sometimes outperform much larger models.
Wait, so you're saying that a smaller model can actually be better than a larger one simply by investing more time in finding that perfect noise?
It highlights the importance of not just focusing on model size, but also on how we use those models efficiently.
Yeah.
This research really challenges the idea that bigger is always better when it comes to AI.
This is already blowing my mind, and we're just scratching the surface.
Yeah.
I'm eager to delve deeper into these algorithms, these verifiers, and how they all work together to achieve these amazing results.
The researchers tested these techniques on 2 datasets for text-to-image generation drawbench and T2I comp bench. These datasets are designed to be quite challenging.
So they're pushing these AI models to create images from very specific prompts. What kinds of prompts are we talking about?
Everything from photorealistic scenes to very complex compositions.
Yeah.
Drawbench, for instance, has prompts that might include things like specific objects, spatial relationships, or even abstract concepts.
And for each of these prompts, the goal is to find that perfect noise that leads to the best possible image output.
That's right. And the paper introduces a whole range of sophisticated verifiers that are used to judge the quality of the generated images.
You mentioned these verifiers earlier.
Yeah.
Can you give me some specific examples of how they work?
They actually use models trained on huge amounts of human feedback and data.
Yeah.
One example is an aesthetic score predictor that has learned to predict how humans might rate the quality of an image. Another is SILIP score, which measures how well the generated image aligns with the text prompt.
So these verifiers are like specialized AI art critics, each with its own set of criteria for judging images.
In a sense, yes. And the researchers combined these verifiers with different search algorithms to find the optimal noise for each prompt.
You mentioned earlier that there's no one-size-fits-all approach.
Right.
Can you walk me through some of the different search algorithms they explored?
One approach they call random search simply generates a large number of noise candidates and picks the best one based on the verifier's score.
Okay.
It's a brute force approach, but
Yeah.
it can be surprisingly effective.
It's like throwing a bunch of darts at a dartboard and hoping one lands close to the bullseye.
They also experimented with more refined techniques like zero-order search, which iteratively explores the neighborhood of a given noise candidate.
So instead of random guesses, it's more like a systematic search, narrowing in on the best option step by step.
The idea is to use feedback from the verifier to guide the search toward better and better starting points.
It's fascinating how they're using these algorithms to essentially navigate through this vast landscape of potential noise candidates.
What they found is that different verifier algorithm combinations work best for different tasks.
Okay.
For example, on Drawbench, which features a diverse range of prompts, a combination of multiple verifiers, including the aesthetic score predictor and clipped score, led to the best overall results.
So for a data set like Drawbench, which requires the AI to be more flexible and adaptable,
Yeah.
a combination of different expert opinions seems to be the most effective approach.
And to make things even more interesting,
Okay.
they introduced an LLM grader to evaluate the images generated for Drawbench.
An LLM grader, what exactly is that?
It's a large language model that has been specifically trained to assess the quality of images based on several criteria.
So they're using one AI to judge the output of another AI.
That's right. And this LLM grader takes into account things like how accurately the image reflects the prompt, the originality of the composition, and even the overall emotional resonance of the image.
That's incredibly sophisticated. It's almost like they're trying to replicate the nuanced judgment of a human art critic.
On the other dataset, T2I Compbench, which focuses more on compositional accuracy,
Okay.
a different verifier called image reward proved to be the most effective.
So T2I Compbench is more about making sure the AI understands the specific details and relationships described in the prompt.
Image reward was specifically trained to capture a broader range of human preferences, including things like composition realism and even ethical considerations.
It sounds like image reward is a more holistic judge, considering not just the technical aspects, but also the overall impact and appropriateness of the generated image.
And one of the most remarkable findings is that even relatively small diffusion models, when given more inference time and the right search strategy, can achieve results comparable to or even better than much larger models that don't use these techniques.
So size isn't everything in the world of AI.
Right.
It's about finding the right tools and using them effectively.
Yeah.
What kind of results did they see with these smaller models?
They compared a smaller model called PixArt with the much larger FLUX.1 dev model by strategically searching for the perfect noise at inference time. PixArt, even with significantly less computational power overall, can achieve impressive results on Drawbench, sometimes even surpassing FLUX.1 dev in certain metrics.
That's remarkable. It suggests that these inference time scaling techniques can be a real game changer.
Right.
Especially when working with limited resources.
The paper also explores how different factors like the number of search iterations, the computational budget allocated to each iteration, and the number of denoising steps influence the results.
So they're really fine-tuning the entire process from the initial search for perfect noise to the final image generation.
One interesting finding is that the optimal amount of compute per search iteration varies. Sometimes using fewer denoising steps per iteration can lead to faster convergence, although the final image quality might be slightly lower. Conversely, using more denoising steps per iteration can result in slower convergence, but a higher quality final image.
This is a trade-off between speed and quality.
It highlights the importance of finding a sweet spot that balances the computational cost with the desired image quality.
This has been a fascinating deep dive into the world of inference time scaling for diffusion models. We've covered a lot of ground from the concept of perfect noise to the intricacies of verifiers and search algorithms. It seems like this research is opening up new possibilities for how we think about and utilize AI for creative tasks.
It's an exciting area of research, and I'm sure we'll see even more innovative applications of these techniques in the future.
Well, thank you for taking the time to walk me through this. I feel like I have a much deeper understanding of how these models work and the potential they hold.